Okay. All right, recording started. Welcome back to the Thursday session for January 21. More probability questions. And here is the copyright notice that we, of course, have to show. There. These are from the free GMAT prep software. Copyright GMAC. If you do submit GMAT prep problems, please make sure they're from the freeware and not from the paid question packs and so forth. And don't forget where you find multiple choice answer options. Okay, let's do one. How about this one? This is a data sufficiency question. So I mean, remember in these sessions we do assume that people have a basic familiarity with the format of data sufficiency and with what the choices mean and so forth. So go for it. Don't forget where the multiple choice answers are found. Give it a shot. All right, we should probably pick a thing here pretty soon. Problem's got a lot of words in it, so if it takes longer, of course, that's understandable. But if you are not genuinely making progress on the problem at this point, you should not still be working on it. Okay, if you are Kate or Ramya or Veronica G or Alex, you should pick an answer to this problem. Again, I mean, make sure you know how this test works too, because you can't not pick answers on this test. So right from day one, you got to school yourself to just pick answers all the time to all the things. I mean, you don't pick an answer on the test, the problem will just sit there and stare at you until you do pick an answer. So you might as well just get used to it and start making things. There's a lot of guessing on this test. A lot of guessing. Even if you're getting a 750 or something, there's still going to be a lot of guessing. In fact, even if you're getting an 800, there's still going to be a lot of guessing. So, all right, let's discuss it. And I mean, apparently, no shame in guessing, man. Here's the class responses here. We're basically all over the place on this one. No majority consensus, nothing, right? Pretty much random responses here. So, yep. Anyway, let's talk about it. So they give you this thing, which it's like a plastic tablet with 5 sheets front and back, so basically 10 pages. It's legal size, 8 by 14 inches or so, and it has graph paper lines on it. So you can theoretically trade it in at any time. So in theory, you have infinite pages, but you wouldn't really want to trade it in except between the sessions, because if you could hold it up and trade it in the middle of a section, but then you would have to wait for the moderators to actually come trade it, and that would be sort of weird. But yeah, it's a lot of space. I mean, unless you have gigantically huge handwriting, you're not really going to run out of space. But you should. I mean, you can buy replicas of it. In fact, I think we sell a replica of it, and if you buy our materials, I think we give it to you with the materials. But you can Google it too. You can still get pictures of it and stuff. It's wet erase, so you should get used to not erasing stuff. But okay, this is a problem. It's got a lot of words in it. It's a word problem. So we've done a lot of sessions on word problems at this Thursday thing, but basically the deal with word problems is people think that word problems are hard because they don't address word problems in a way that makes sense. Like a lot of people try to solve word problems without setting them up or organizing them, and that's why they find them hard. So you do with word problems, what you got to do first is figure out what's going on and organize them. Organize first, then solve. I mean, that right there, that's the reason why people think word problems are hard, quote unquote. Because they don't organize first. I mean, if you think about it, because in the real world, people find word problems, so to speak, much easier than other things. You know, like if you have to do a spreadsheet of something, then it'll be a lot easier than if you were just plugging things into random formulas. But the reason why it's easier is because it's a spreadsheet. It's a thing that you organize first. So, I mean, think about the way that you make spreadsheets, right? Like when you first make a spreadsheet, it's empty. Of course it is, spreadsheet, right? So organizing a word problem first is a lot like making an empty spreadsheet. If you think about what you do and don't think about when you make a spreadsheet, this should make perfect sense. I mean, you have to think about what should be the column and row headings, like what stuff goes into it, what stuff doesn't go into it, and how does it all fit together. I mean, those are things you think about. You don't think about solving problems yet, right? So let's talk about organizing this first. I mean, what's even happening in this problem? How do you all organize this problem? How could you organize it? Like, what's relevant in this problem about the balls? So we have colors and we have numbers. That's true. Although, what about those colors and numbers is actually relevant? Yeah, about numbers, we only care about evens and odds, because those are the only things that matter in the problem. And then what's the only thing that matters with colors? I'm not sure what you mean by we don't have a split. Yeah, you only care about white or not white. Exactly. Like the difference between red and blue is not relevant anywhere in this problem. Right? If you think about it. Because this is what you do, and you can only do this if you are not also trying to do math at the same time. I mean, if you're trying to solve the problem at the same time, there's absolutely no way you're going to be able to make these realizations. You're just going to be overwhelmed, right? But if you're just thinking about organizing the problem, just, you know, we're not doing math yet, right? No math right now, no numbers right now. I mean, just think about, just look at what actually matters. Just look at what things actually figure into the problem. So if you look at this, basically you're just going through the words and seeing what actually plays a role in the problem. Because they mention numbers 1 through 10, but you're not using the numbers 1 through 10 per se, because they're not doing anything based on that. Like here's even. And then here's even again. And then here's even again. Even is the only thing they do with numbers. So with numbers, all that matters is even or not even. And then you also have the idea of what color the ball is. So that's white, and that's white, and that's white. And so that's all that matters in the problem is white or not white. Hey, look at that. In other words, this problem fits perfectly into what category of problems? It's this thing or it's not this thing, and it's also that thing or not that thing. That's perfect template of what type of problem. Yeah, exactly. It's an overlapping sets problem. It's perfect, right? And if you try to solve it too early, then you're just not going to figure that out. But if you realize that you don't try to solve it right off the top until you set it up, that's when you'll make these realizations, because you let yourself make them first. Yeah, right? This is absolutely an overlapping set problem. Sure. So in other words, it's almost not even really a probability problem at all. In fact, it's not even a probability question at all. I mean, in a sense, it's kind of ironic that we're even doing this in today's session, considering that today's session is a probability session, because you have 25 balls. So what is the probability is kind of not even really probability. You guys see that? Since we have a known number of balls in the box, what is the probability is equivalent to just asking what? Yeah, you could just ask how many, right? Those are interchangeable questions. Like probability of 4 out of 25, same as saying you got 4 balls. Probability of 7 out of 25, same as saying you have 7 balls, and so on. So in this context, at least, this is equivalent to how many coming over white. So yeah, overlapping sets problem. All right. Overlapping sets grid. Let's make one. In fact, how many grids should I make? How many physical grids should I draw? Nobody? I mean, how many of those, though? How many of these grids? How many copies of this? Nobody's got an opinion on that. $25 different copies of that grid? All right, Ben's closer to it. Yeah, not, because, okay, I mean, the thing is that a data sufficiency problem is not a problem. I mean, you got to realize this, but every data sufficiency problem is actually 2 totally different problems, because you have statement 1, which is a problem, and then you have statement 2, which is a totally different problem. And then each of these has stuff in it that the other one doesn't. You don't need 3 copies because you don't, if you combine the statements, you could import stuff from one chart into the other, so there's no reason to make a 3rd one. You could just keep one of them and then, right? But I mean, a lot of people just make one chart, and I'm not really sure what they're planning to do once they finish with statement 1 and start with statement 2. Like, are they just going to scratch everything out? And you know, that seems a little suboptimal, right? So yeah, you should make 2 copies of that, and that should not just be overlapping sets or probability or what have you. That should be for absolutely every single data sufficiency problem that ever takes any chart ever. So absolutely every single one. So anytime at all for any data sufficiency problem that uses a chart or diagram or list or grid or any visual aid. Make 2 copies of it, 1 for each statement. Because remember, you are solving 2 distinct problems. That's the thing. I mean, statement 1 and statement 2 are actually different problems. I mean, they're asking you the same punchline at the end. The question is the same, but that doesn't make them the same problem. They have different premises and everything. So don't forget that. Okay, so there we go. And then, last but not least, you gotta figure out what the goal is here. So, okay. What's the probability? So we don't need what's the probability anymore. We can just do this with how many balls. So we can just make this 25. In other words, this is numbers of balls. This is statement 1. Okay. What's the goal? What are we trying to find in this grid? So what I'm going to do real quick, I'm going to put letters in these boxes. And then here, let's just say A, B, C, D, E, F, G, H, I. Okay. Which letter box or boxes is or are the goal? Not C and G. Because if you got anything that is white and also even, then that's going to be weird. It might be C plus G minus A. Yeah, maybe. I think that could be. It is actually, yeah, it is C plus G minus A. But like in terms of actually which boxes it is, I mean, I think you all are trying to be, well, I think you all are smarter than me, but Lynn, you're definitely smarter than me. But if you just think about which boxes actually are white or even, then it's just, okay, well, these ones are both. These ones are white, at least, and these ones are even, at least. So those 3 boxes are the goal. If you do C plus G minus A, as Lynn says, then you actually get that same thing. Because C is just A plus B, and G is just A plus D. So after you add those, if you subtract A, then that's what you'll get. But this is the goal, right? That's the same as that. So, or you could do it as, Look at what's going on down here. Look at this. Does everybody see how it could be this? I mean, to see this, you got to have a certain intuition about how these grids work. So, in these overlapping set grids, remember that the third row and the third column are totals. So, everybody individually is going to be in here somewhere. Like these 4 boxes are all of the individual balls in the box. So, in other words, every ball is in here or here or here or here, and then all the stuff on these margins is going to be totals. So, the problem is asking us for these 3 summed up together, but we know that there's a total of 25 balls in the box. So we could just find that instead, because the goal is just 25 minus that, right? Like it's kind of abstract because we're thinking about even and white, right? But like let's say that you had a room full of boys and girls with long hair or short hair, right? Like if the question said, let's say you had 100 kids in the room, and the question was how many either are girls or have long hair, right? That's everybody except for the boys with short hair. So you could also just do 100 minus however many short-haired boys there are. And if this were a data sufficiency problem, you could actually just find how many short-haired boys there were, because it's data sufficiency, and we don't care if it's 100 minus blah versus whether it's just blah thing. So you could do that, right? I mean, the first step is just to realize that what they're asking for is these 3 red boxes here. And I mean, I think it's kind of important to not be too smart about that in the first place. Like if you're thinking about this as C plus G minus A before you're just thinking about it as this and this and this, then that seems like there's kind of a problem there. I mean, maybe it's just me because I think in very simple terms about things. But you know, you should try to think of things literally first if you have trouble figuring out what goals are in problems like this. So, like in these problems, it's just, okay, well, they want these and these and those. And then you can think about stuff like that. So, goal is you could just find that blue box for the same reason you could just find the short-haired boys if they asked you for this compound of girls and or short hair. So, smiley face if this makes sense. Smiley face. Okay, cool. I mean, so actually this may be the hardest part of this problem, is just knowing what they're even asking us for. So, because that is a little bit obnoxious, right? So statement 1 is telling us that there are no balls that are both white and even. So statement 1 is telling us there's 0 here. And that's kind of it. That's all that statement 1 is telling us. So that's not sufficient. There's still a whole lot of unknowns going on there. Statement 2 So statement 2 is in terms of probabilities. And we got everything else in terms of numbers of balls here. How can we do that in terms of numbers of balls? What does statement 2 mean about numbers of balls, count numbers? Thomas, that's a thing, and what is equal to that thing? I mean, sure, that's 5, but what is 5? Like 5, what is 5? Careful. The word maybe the word minus got past you there. What you can do with this, because it's not white balls with even numbers. It's that's a difference. So, I mean, let's just go ahead and write this literally in terms of what they give us. So the probability that the ball is white. Yeah, let's just straight up do it like that. Let's just write formulas for these things. So that formula is white over 25 is what it is. Minus is minus. And then this probability is even over 25. You can just write that in formula, right? And that equals 0.2. So, and then we can just multiply both sides of that by 25. So even you don't necessarily need an intuition about this. You can just write the exact fact they give you in terms of those fractions. And then you can just multiply those fractions by 25. So let's do that. And if we do that, we get white minus even equals 5. So there is 5. Thomas, there's your 5. But what that is actually the number of whites minus the number of evens. It's 5. It doesn't really tell us about how many white and even there are. That could actually be quite different things. But it just tells us that there's a difference there. So we know that there are 5 more whites than evens total than evens. That's what that means. Other than that, we don't really know a lot, right? So, I mean, that's going to be that's not going to be sufficient here, but we can at least, I mean, we could say that there's E number of evens, and then that would make there be E plus 5 number of whites. And then we can subtract. We can do subtraction there. If you do 25 minus E. And then 25 minus E plus 5 would be what? 25 minus E minus 5. Okay. So you can do that. That's not going to tell us what any numbers are, but at least it gives us a thing. So not sufficient though. Can't find anything. All right. What are they assigned randomly? What do you mean by that? Um, hmm. I mean, okay, I'm going to try to answer this without going into a long digression, but I think you have some misconceptions about the word random because, I mean, first of all, we have a set of balls that are sitting in a box, and the balls are already printed with numbers. I mean, it's not like, the problem is not you print new balls at random, and like there's just a pre-printed bunch of balls. So whether they were printed at random or not kind of doesn't matter. But on top of that, if you printed 20 balls at random, then the chance that exactly half of them would be even would be a really small chance. I mean, that would almost definitely not happen. You know, like imagine flipping a coin 20 times. I mean, the chance that you would flip exactly 10 heads would be very small. You know, same sort of thing. Because randomness is, you know, randomness. There'd be a whole bell curve of distribution there. And very few of them would have perfect symmetry. So, you know, yeah, that. I mean, regardless what Sank said in the chat box. I mean, so regardless of that, it really makes no difference because that's irrelevant to the problem. I mean, you have a set of balls. They could have been printed at random. They could have been, you know, given to you by a god on top of the mountain, and it still doesn't matter. They're just balls with numbers on them. But also, that's not even sort of what randomness means. So we could be careful of that. So, but you just have a set of balls, and they have numbers on them, and that's what you have. Okay. We have this. This is the thing. This is insufficient. Any questions about the individual? I mean, well, they can't be half. I mean, there's 25 balls. So you know right off the top that can't be true. I mean, how could you have 12 and a half balls with even numbers on them? So there goes that, right? I mean, you should have thrown that one out right off the top because you have an odd number of balls. So there you go. All right, statement 1 or statement 2. Any questions individually? All right, then together. So this is if you have the this is why you don't need a third copy of the diagram, because now you can just import whichever would be less work to import. Here pretty clearly that would be less work to bring over. So if you bring that over, then all right, e plus 5 minus 0, and then e minus 0. And then we can also use rows and columns here. We have this column here. So if we use that column, then we get 25 minus e minus e plus 5. That would give us 20 minus 2e. And then the only thing we haven't used yet would be this row. If we try to use that row, then it gives us e plus 20 minus 2e equals 20 minus e. But you know what that just winds up giving us? Just winds up giving us 20 minus e equals 20 minus e. You know what that means? It means your statement's not sufficient. Now, if you don't like that, what you could always do is you could always plug in numbers. Because, I mean, this actually is a proof that the statement is not sufficient. On the other hand, if you are like me, it probably doesn't feel like one, and it probably doesn't satisfy you very much. Because, I mean, it doesn't really, testing cases, right? Because it doesn't really look like like you've proved anything here. So what you can do instead is or in addition, not necessarily instead, is you can just start tossing numbers in there, right? Like if you have 5 and 10 here, then you can just work out the numbers, right? So this would be 10, and this would be 5, and this would be 15, and this would be 20, and 10. And then if you can get it to be another number, then you have definitely proved insufficient. So if we make this like 10 and 15, okay, well that'd be 15. That one actually be 10. And then this would be 0. And that works too. So that proves it not sufficient for sure, because we actually have 2 different cases of numbers here. And notice how not long that takes. You know, if you get to the end of this work and you're like, I'm not really sure about that, this took an extra 20 or 30 seconds. And that was an extra 20 or 30 seconds with me talking through it, which means it would take you even less time than that. So still not sufficient. It's going to be E elephant. But the point is not to be afraid of switching methods in the middle of stuff. Like even after you've been a couple of minutes and whatever, if you need to switch to another method, then you switch to another method, and that's what you do. Because like algebra is very, very bad at proving not sufficient, as you see here. In fact, it doesn't work. That's kind of the whole point, right? And like algebra only proves things when they're sufficient. It doesn't prove that things are not sufficient. It just kind of doesn't do anything like it did here. So if you wind up with this I'm going around in circles situation with algebra, then don't keep running around in circles. Just switch to something else like testing cases. That's a big lesson here. Yeah. I mean, algebra wastes a lot of time for a lot of people because they don't know when to stop doing it. Big lesson there. Make sure that you know when to stop with the algebra. Any questions about this? Lots of little cool lessons with this problem. And there's a lesson about organizing it first. Makes it easier to see what kind of problem you're dealing with. There's the lesson about making 2 diagrams. There's a lesson about just literally translating statements if you don't know what else to do with them. There's the lesson about interpreting these grids. There's a lesson about switching between algebra and testing cases. There's like a billion things to learn. It's pretty neat. Okay, cool. Let's do another one. What about that one? The data sufficiency. All right, should be picking something here. Picking a thing. In terms of making guesses, remember that's how this test works. You have to make a guess. You can't not make a guess. And here's where we stand right now. That's where we stand. Yep. That's where we stand. So, in other words, you should not feel bad about making a guess. Although, it's interesting because well, that majority answer is an answer that you all shouldn't be picking. But go into that in a second. Here. Let me throw something at y'all. See what you get with this. Is here. Okay. What is the only thing that could not possibly be the answer to this question? Does anybody know? Out of A, B, C, D, or E? There's only one choice that could not possibly be the answer to this. Does anybody know which letter that is? That's it. That's the letter. Could not possibly be C. It could be any other letter. Yes, it could. I mean, this might just click with you. It might not. I can just show you answers of the other ones. I mean, it could be A, here, sure. Like if it was something like, is X greater than 10? Statement 1, X is greater than 12. Statement 2, X is greater than 8. Okay, sure. That's A. B, just, switch the statements of that last one, right? D, okay, is X greater than 10? Statement 1, X is greater than 8. Statement 2, X is greater than 6. Sorry, that'd be 12 and 14. Let's make them. That's D, because either one of them is greater than 10, right? And then E could be, just make them both something less than 10, right? Is X greater than 10? Statement 1, X is greater than 6. X is greater than 8. Okay, but the point is this can't be C, because if you have two, kind of healthy, right? Like, if I tell you that X is greater than two different numbers, then one of these is going to be a stronger statement, and one of these is going to be a weaker statement. And so one of them is just going to, when you combine these, one of them is not going to matter at all, is the point. So, can't be C. It could be E, because they could just both not do the thing, right? But the answer can't be C. So, smiley face if this makes sense. In fact, you know what? Hey, there. The answer to that question still can't be C. Still impossible. It doesn't even matter what the question even is. Nope, still not even a thing. I mean, now the answers down there don't necessarily illustrate in full generality, but it is impossible for this to be seen. Because the point is that these can't help each other out. Like, say, when you combine the statements, if the answer is C, that means, intuitively what that means is that in some way the two statements have to contribute to each other in a way that, like, each one has to contribute something the other one doesn't contribute. Because that's what it means to pick answer C. Like, if one statement just overshadows the other one, then the answer would be either A or B. So, yeah, right? I mean, there's no way that, like, whatever is the larger number is going to be a stronger statement, right? So these statements can't both contribute. It's impossible. So, nothing. So in terms of this, it's not as obvious as that, but if you think about this, okay, because statement 1 just means that you have 6 or more women, right? So that's what that means. I mean, that should be clear enough. But statement 2, if you think about this for a second, statement 2 is going to be another inequality that says that women is greater than or equal to some number, right? This is just going to mean women is greater than or equal to some number. And this is just whatever number where that starts happening, right? Wherever like wherever you have enough women to make that probability less than 1/10. Because I mean, the more women you have out of 10, the smaller that probability goes. So we don't know where that value is, which is why this problem is a problem, right? This is why this problem even exists as a problem in the first place. But this is totally that kind of inequality. I mean, smiley faces, that makes sense to y'all. Because the more women you have, the smaller the probability of two men is going to go. So you are looking at a situation that is exactly like this one, which means that it is totally impossible for the answer to be C to this question, even if you don't comprehend the question part at all. You know the answer is not C. Not even sort of possible. So if you have C for this, you should guess another answer to it, which you should do now. (1/20th)? What if I mean, nothing is supposed to be 1/20th in this problem. But okay, there's 3 people who still have C as their answer. Remember, we just showed that it can't possibly be C, so you should definitely unpick that and pick something else, even if it's a random guess. Okay. So let's take a look. So yeah, probability. I mean, they define this letter P, which is kind of, there's not really a need for this letter to exist, right? You just want to know. The question is the probability of 2 women greater than 1/2? So all right. There's a bunch of ways that you can approach this, by the way. How do you calculate the probability of 2 women? Yeah, you do what NSL is doing there, which is also what Thomas is doing in algebraic form. T, you can turn off those default chat icons by going to Tools and then Chat. I don't know why those are enabled by default. It kind of annoys me that they are, but that is, you can disable that. Yeah, it's going to be however many over 10 times however many minus 1 over 9, right? So what you can do, and like what NSL is doing is just doing it for a particular case of 6, right? So it seems like a decent way to do it to me, right? So you can just say number of women and then probability of 2 women. Sure. All right, let's just do that. If you have 6 women, then the probability of 2 women is 6 over 10 times 5 over 9. And that is what it is. So 5 and 10 give you a 1 and a 2. So that's, and 6 and 9 is 2 over 3. So that's 2. So that's going to be 1/3 once you break it all down. Right. Do you have, okay, this is 1/3. What does this mean about the more than half is 6? Easiest, no thought required test case. What do you mean by no thought required test case? Interesting that you would say that. Order, when you multiply probabilities together, order is always a thing. You actually can't multiply probabilities without order being a thing, but there's no order here because woman, then woman there's only one way to do that. If you had a woman and a man, you would actually have to do that in both orders. You'd have to do man, woman, and then woman, man. Okay, right, but the result is not super obvious though, right? Probabilities are not necessarily that intuitive, is what you're saying. Yeah, okay. So notice this is less than 1/2. Okay. What does that mean about the sufficiency of that statement? So this means if you're saying sufficient, then whoa, back up. Definitely got to make a device to remind yourself of what the goals are. We've done some of these Thursday sessions on yes/no format data sufficiency questions, in which we introduced this device. For setting this up. I mean, remember you have this yes case and you have this no case. If you can make them both happen, then that's not sufficient. The yes case here would be that you can get the probability to be more than 1/2. The no case would be that you could get the probability to be not more than 1/2. If you can make both of those happen, then it's not sufficient, right? So just make sure that you set this up on your paper. Because then you won't, number one, you don't have to keep reminding yourself what the goals are. And number two, you won't forget about it. So okay, sure. So statement 1, statement 2, and then both if necessary. So we made this happen right there is what we did. So, I mean, can we get the probability to be more than 1/2? Yeah, sure we can. We can just have 10 women, dude. I mean, we could calculate a bunch of crap if we want to, but who wants to do that? I mean, if you know what this goal is, then there's no sense in wasting the time. I mean, if we want the probability to be greater than 1/2, we can just make all women all the time. And then the probability will be 1, and then we can just get that without having to waste all that time. So, yeah. So if there are 10 women, then the probability of 2 women is 1 without having to calculate it. So this is not sufficient. But if you said sufficient to this, it's because you forgot what you had to do to get not sufficient. And that's a common thing. It happens all the time, even to people who've been studying this stuff for months and months. So remember that you should set up any data sufficiency problem of the yes/no type. You should always set it up like this. Don't take the chance. Just do it. If you can check off both boxes like this, then it is not sufficient. Also, make sure that you're not thinking in terms of the word yes and the word no. That's the other big mistake that people make. Those are not things. You don't make those happen in a problem. You don't pick numbers that say yes or numbers that say no. You pick numbers that give probabilities like this. So make sure you translate yes and no into those workable things. So, okay, smiley face if this makes sense. Someone gave me the other face. Okay, if you can explain why other face, that would help. You can use 6 women because when you have 4 men, the probability is 2 out of 15. We are talking about statement 1 right now. I think you're looking at statement 2. But let's do that. Okay, by the way, for statement 2, we know for sure that we can check this box. Because, I mean, you can also, if you have all women again, then that clearly satisfies statement 2. Because that would give you a 0 probability of the problem of selecting 2 men, right? If you have 10 women, then probability of 2 men is 0. So statement 2 is satisfied. And this box is checked. So the goal becomes really, can we check this box or not? So if you have 6 women, so let's just extend the chart, right? What we need to do is figure out whether we can, right, we need to extend this into the probability of 2 men to check, we need to check whether statement 2 works, basically. So this is just checking the validity of statement 2, which is what HW is doing there. So if we do that for 6 women, then that means there's 4 men. So that would be 4 over 10 times 3 over 9. And that is 12 over 90. We don't have to reduce the fraction. That's more than 1/10. So yeah, so that doesn't work. You're right. Okay. So yeah. So you just try 7 women. See how that goes. 7 women. And we should check this first, because if this doesn't work, then there's no point, right? So if we check that, then that would be 3 out of 10 times 2 out of 9. That is 6 out of 90, which is less than 9 out of 90. So that's less than 1/10. So this is a check that statement 2 works. So now we can check the answer to the problem. The probability of 2 women is 7 out of 10 times 6 out of 9. And that is 42 out of 90. That is still less than 1/2, because 45 is half of 90. So we check the box. So it's not, because it's not a restatement of statement 1, because statement 1 includes 6 women and statement 2 doesn't. And if this were a couple of 90ths higher, then it could have made all the difference, right? Because like if this fraction was 4/9 in the question instead of 1/2, then the answer to the problem would be B instead of E. It'd be B boy, because this is more than 4/9, but that isn't. So it's not an exact restatement. And that, again, these threshold values make a difference here. But this is less than 1/2, so this is still not sufficient. And both of these cases are going to carry over to the two statements together. So yes, you are correct. You cannot have men equals 4 in statement 2. That's why we crossed it out here. You got to have the most men that you can have there is 3, which even with 3 men, now that's still enough to make probability P less than 1/2. So they're not quite the same, right? Statement 1 is you have anywhere between 0 and 4 men. And statement 2 is you have anywhere between 0 and 3 men. So that they're close to being the same, but they're not exactly the same. And as you know, in data sufficiency, those borderline cases can make totally all the difference in the world. I mean, here they don't, but I mean they certainly could and do all the time. So these cases both work for both statements as well, because you could have 10 women in both cases, and you could also have 7 women in both cases. So still going to work for both. E, elephant. Look at that. Good stuff. As far as takeaways from this one, the biggest deal here, because these probabilities are not hard things to calculate. And I mean, notice you don't really have to reduce all these fractions either. I mean, in fact, the time that I spent reducing this fraction up here was kind of a waste of time. We could have just left this as 30 out of 90. Because you only had to see that this was less than 1/2, which you could easily do without reducing it. So there's a lesson there too. I mean, any time spent reducing fractions here would have been wasted. So the biggest lesson here, again, is organize your work. I mean, when you have the yes/no style of questions, really just make this device, make it every time. There's really no reason to not make it. You know, just right off the top, make it. It'll help you organize your thoughts. It'll remind you what the goals are. Because, you know, these are not, the reminding yourself thing is a very important thing, because these are not organic to the problem. I mean, the problem, this doesn't happen in the problem. Like, P doesn't jump out and turn into a half or not. Like, these are things that you have to check yourself. They don't emerge out of the problem. So if you don't write this down in a device like this, you're going to have to keep reminding yourself of it over and over and over again, which is really hard to do. I mean, that's a lot of brain power wasted on that. So if you just make the device at the start of the problem, then you win the game. All right, just coming up here on time. Kate, I see you have some text in your text box. If you have a question or something, try to grab that. No text. Yes, text. All right. Other than that, I think that about does it. Thanks for stopping by. And now we're going to be back to our usual bi-weekly schedule here. So this was just this consecutive weeks thing was only because we had a relatively long hiatus in between. So we're going to be back to roughly every other week I think it's exactly every other week for a couple of months here. So, thank you. And, all right, thank you for attending. Good afternoon, good evening, good night, good luck. And we got the next session here in about 2 weeks. I sound like I did in 2011. Well, you know, I mean, people's voices, man, they don't change too much after puberty. Puberty was about 30 years ago for me. So, yeah. Okay. All right, gonna kill the recording here.